Pneumatic power, let's do it. Make sure you've looked at the Google Doc so you know exactly what you're looking for in the video. Remember, I talk faster than you type. I talk faster than you write, and that is what the pause button is for. All right, pneumatic power, here we go. So pneumatics is the use of gas flowing under pressure to transmit power from one location to another. Basically air moving through pipes and tubes to do things. Gas in a pneumatic system behaves like a spring since it is compressible. That is very true. We grab a balloon and squeeze it, right? We are squeezing or compressing that air. If you fill a syringe full of air, right, we can compress it. So air is compressible. That's going to be important to know. Pneumatic systems use a compressible gas. We just said that. They possess a quickier, jumpier motion. They're not quite as precise. They require lubricant usually. They're generally cleaner. Often operate under a pretty low pressure, 100 psi, and generally produce less power. We don't use these for really heavy lifting jobs. We'll use hydraulics for that. Some early pneumatic uses. This is a picture of a bellows that you might use to heat a fire, or a blacksmith might use to get some iron really hot. So we have kind of this rubber-ish type membrane that connects these two pieces of wood together. It lets air in. We push it. It lets air out. This was one of the first times we were thinking about harnessing air and doing something with it. Another example was America's first subway. This is in New York City. And if you notice, it didn't last very long, and it was only 300 feet. But imagine pushing air through this tube and moving people from point A to point B. New York subways have certainly come a long way since then. Modern examples, probably the best one are robotic arms. We use pneumatics, little suction cups on the end. We'll use air to grab something or suck onto something, to lift it, to move it, and we have robots do that all the time. From automotive factories to lifting and placing items in a box. Pneumatic end effectors are what they're called, or the arm or the kind of hand, the resulting part of what that robotic arm is used to do. Those are used everywhere in industry and engineering. Another example is like if you've gone to the bank drive-through, we put the little tube in here, or the little cylinder goes through the tube, goes inside to the teller. Great example. Just a really simple pneumatic cylinder. We put air in, we push it out to do all kinds of things, to crush a can, to press a part onto a fitting, to press a label, lots of different uses. All right, properties of gases. They are affected by three variables: temperature, capital T; pressure, lowercase p; volume, capital V. Reminder, gases have no definite volume. They are compressible, and they are lighter than liquids. Properties of gases. Let's continue. Let's talk about absolute pressure and gauge pressure. So if you're not aware, there is the force of air on your head right now where we are in the world. And that is about 14.7 psi. If I run up to the top of Mount Everest, I have less pressure on top of me, and there's less oxygen in the atmosphere. At that point, it's spread out, it's less dense. That's why I have a hard time breathing up there. And this idea, we have to figure out what the absolute pressure is on a system. So the way we do that is very simple. We just add atmospheric pressure to our gauge pressure. Really easy. So I might have a gauge on my air compressor in the fab lab or in my garage, and it says 120 psi. If I want to know the absolute pressure, all I do is add 14.7. Super simple. And I get 134.7 pounds per square inch, or psi. So that's our concept of absolute pressure. One other conversion we need to know about is absolute temperature. 0 degrees does not represent true zero. Absolute zero is where there's no molecular movement, and that's negative 460 degrees Fahrenheit. Absolute temperature is measured in degrees Rankine, and that's a scale that engineers use sometimes for just this purpose. Degrees Rankine is just degrees Fahrenheit plus 460. So we can't have negative temperature because we could then end up with a negative pressure. So what we end up doing is using this degrees Rankine scale. Quick example, if the temperature in the air system is 65 degrees Fahrenheit, what is the absolute temperature? 65 plus 460 is 525 degrees Rankine. All right, almost done. Pascal's law. Pascal's law is pressure exerted by a confined fluid acts undiminished in all directions. Pressure is the force per unit area exerted by a fluid against the surface. This makes me think of swimming in a swimming pool. If you have ever been in the deep end of a pool, you feel that pressure. And the reason you're feeling that pressure mostly in your head is you have these air cavities or these sinuses right behind your cheekbones. So it's where you feel that a lot. And if we read that definition again, understanding that pressure is exerted by a confined fluid, which is our swimming pool, acts undiminished equally in all directions. So it's pushing on my body in all directions. I happen to feel it in my face and maybe in my chest because my lungs and my sinus cavities are filled with air, and we know air is compressible, so it's kind of giving some force to those. That's why it doesn't feel all that great. Okay, Pascal's law is P equals F over A, pressure equals force over area. P is pressure, which the units are pounds per square inch or PSI. F is force, our unit is pounds. A is area, and square inches is our unit. Let's do an example, and then we're done with this part. All right, here's my picture of a cylinder. This is really similar to our picture back here of a cylinder, except we have a cutaway view, which is great to help with understanding all this. So we have a picture of a cylinder. The diameter is 3 inches across. We are putting 50 pounds of force. And our question is asking how much pressure can be produced with a 3-inch diameter cylinder at 50 pounds of force. Great. So our formula for Pascal's law, P equals F over A. So I'm going to need to find the area. I am given my force, and then I can find the pressure. So we know that area is pi r squared. I can get the radius of my circle of my diameter. My diameter is 3, so my radius is 1.5. 1.5 squared times pi gives me 7.1 square inches. And I take that number and I put that into my pressure equation, P equals F over A, or P equals 50 pounds over 7.1 square inches. Remember, I was given 50 pounds as my force. I do my math and I get 7 pounds per square inch, or 7 psi. All right, I think that's where I'm going to stop this video, see what your instructions say for the next one.